Step 1. Raw silicon extraction. The journey begins with quartzite sand, one of the most abundant materials on Earth. In massive electric arc furnaces, it's heated to over 2000 degrees Celsius, where carbon reduces the silica to produce metallurgical-grade silicon. This silicon is 98% pure, not yet clean enough for electronics, but it's a start. Step 2. Ultra-Purification process. The raw silicon is converted into trichlorosilane gas and purified through fractional distillation. This gas is then decomposed on heated rods, depositing semiconductor-grade silicon with a purity of 99.999999%, known as 9N purity. That's one impure atom in a billion. Step 3. Single crystal growth. Using the Czochralski method, a small seed crystal is dipped into molten silicon and slowly pulled upwards, rotating as it goes. This forms a flawless cylindrical ingot up to 300 mm in diameter and weighing over 300 kilograms. The process takes up to 2 days of precise temperature control. Step 4. Precision wafer slicing. Diamond wire saws slice the ingot into ultra-thin wafers, each only 725 micrometers thick, thinner than a human hair. A single ingot can yield thousands of wafers, each one requiring near-perfect flatness and parallelism. Step 5. Chemical-mechanical polishing. The sliced wafers go through multiple polishing stages. The final step uses colloidal silica to achieve atomic-level smoothness, less than 0.1 nanometers of surface roughness. Even the tiniest defect here could ruin entire chips. Step 6. Ultra-clean processing. Now inside Class 1 cleanrooms, 1,000 times cleaner than hospital operating rooms, the wafers are cleaned using special chemical solutions that remove every trace of organic or metallic contamination. A single dust particle could destroy thousands of transistors. Step 7. Thermal oxidation. The wafers are heated again to over 1000 degrees Celsius in pure oxygen. This causes a thin layer of silicon dioxide to form, an essential insulating material just nanometers thick that will protect the underlying transistor structures. Step 8. Photoresist coating. A light-sensitive polymer called photoresist is spin-coated onto the wafer surface at 3000 rpm. This creates a uniform layer just 100 to 200 nanometers thick. Any unevenness could lead to distorted transistor features. Step 9. Photolithography. Deep ultraviolet light, just 193 nanometers in wavelength, is projected through a mask onto the wafer. Immersion lithography, using a thin layer of water, enables feature sizes as small as 5 nanometers, smaller than a strand of DNA. Step 10. Chemical development. The exposed photoresist is chemically developed using a developer solution, revealing precise circuit patterns. Timing is controlled to within tenths of a second for consistency across the entire wafer. Step 11. Reactive ion etching. The revealed areas are etched away using a plasma of fluorine ions at sub-zero temperatures. The process creates straight, vertical trenches with atomic precision. Every layer must be etched with nanometer accuracy. Step 12. Resist removal. Remaining photoresist is stripped away using an oxygen plasma. This process must be 100% complete, even a small residue could interfere with the next steps. Step 13. Ion implantation. Dopant atoms like boron or phosphorus are accelerated and embedded into the silicon at energies up to 50,000 electron volts. This forms the N-type and P-type regions essential for making the transistor function. Step 14. Activation annealing. The wafer is then heated once again, typically to around 1000 degrees Celsius, to activate the implanted dopants and repair any crystal damage caused by the ion implantation. Step 15. Gate electrode creation. Ultra-thin layers of polysilicon or metal are deposited and patterned to form the gate electrode, the part that controls current flow in the transistor. High-K dielectrics like hafnium oxide are used to minimize leakage. Step 16. Metallization. Copper is deposited and etched to form the wiring layers that connect each transistor. Modern chips use over 10 metal layers, with wires just 20 nanometers wide, thousands of times thinner than a human hair. Step 17. Protective passivation. A final layer of silicon nitride or silicon dioxide is added to protect the chip from moisture and contamination. This layer is hermetically sealed to ensure the chip remains functional for decades. Step 18. Wafer-level testing. Each chip is tested using microscopic probes that measure critical electrical parameters, from switching speed to leakage current, all while the chip is still on the wafer. Faulty dies are marked for removal. The wafer is cut into individual chips using diamond saws or lasers. Depending on the design, each wafer can contain hundreds of processor chips or millions of memory cells. Step 20. Final packaging. Good chips are bonded into protective packages using gold wires or copper pillars. These packages allow the chip to interface with the outside world and protect the delicate silicon inside. Conclusion: the finished transistor. From sand to silicon, from raw material to precision-engineered microstructures, over 200 steps come together to produce a single transistor. Billions of these are packed into every processor, each capable of switching billions of times per second, powering the digital world we live in.